Welcome to the next session of this Swayam course on Cornerstone Ideas in Material Science and Engineering. I'm TIJU Thomas and I will be continuing this session. I'll be in charge of this session. So as you can see, we have decided to conduct this session in a different setting. Earlier, the classroom that we occupied was in the Teaching Learning Center, IIT Madras. This one is in the Electrical Engineering Department, a hall called the Malaviya Hall. I would request you to take a scan of this and show the people who are the audience so that they see how this room is designed. So you will find that there are places where students can go and write on the board. That is how this was deliberately designed. So a teacher can actually facilitate a Q&A session where students can go write on the board, brainstorm together and so on. And there is also a projector, conventional style, and there is a podium and so on. So a setting like this also would be largely very helpful wherever you are working. Not only that, if you look behind, you will find that there is a slide board that allows a teacher to write, slide it down and write more. Okay? And as a consequence, a combination of these settings that are actually provided, this infrastructure is also somewhat conducive for interactive education. And you can also see the kind of tables that have been used here. You will notice that tables can be set in a larger setting such that you can have larger groups, or you can actually set it up individually so that you can have smaller groups. So you have a small group sitting here, you have a mildly larger group sitting here, and you can facilitate this. So the classroom setting doesn't become static, it becomes a dynamic setting. So coming back to lessons as far as teachers are concerned. So these are some of the things I have asked you. A snapshot of this would be helpful. So please recall some of these things that we have discussed in the class. What does it mean to create an interaction-friendly teaching learning environment? Also, do we give enough time to the students to consolidate their lessons? And finally, what does it mean to do large classroom management in the context of active cooperative learning? These are all rather meaningful questions to ask ourselves. Okay? And these are some of the new terms that you must have heard in the context of active cooperative learning. The first one is pedagogy, andragogy and heterogogy. So pedagogy is essentially the discipline that focuses on the methods that can be used to introduce a subject in a rather streamlined manner. Andragogy is the discipline that deals with adult education. This is particularly relevant for university educators, and how a subject matter can be actually streamlined in the context of young adults, considering the way they absorb information, consolidate information and so on. And heterogogy, which is an increasingly important term, and that is for self-directed learning, and as I have told you, it is very relevant for MS PhD education in particular. All right. The next one is teaching learning environment. This is something I have been emphasizing almost every class, almost every session. And I have been talking to you about the setting that we have created here in IIT Madras and how we believe it will actually help in creating an interactive atmosphere. Active cooperative learning and think, pair, share, they are related concepts. So you can see that active cooperative learning is enabling students to talk to one another, learn from one another, share their experience with one another. And this goes hand in hand with think, pair, share and guided reading, writing and learning. You would have noticed that I usually give some handouts. I ask people to look for some specific information in that particular handout and respond, so that there is some active engagement with the material and not just passive listening. Then participatory learning, which is basically making the student in charge of her own or his own learning. And of course, teaching learning environment. I apologize for bringing it twice here. So I'll just delete it. Today I want to talk about scaffolding. Scaffolding is the idea of creating a structure for the students around which they can build information and knowledge base for themselves. And in today's session we will be using a graphing exercise in order to teach students to think about mechanical behavior of materials. Alright. So this scaffolding exercise that I will be giving them will enable them to think about stress strain curves and mechanical behavior of materials in particular. There is no background information that is required because I will walk you through this in a very, very gentle and scoop-sized manner. Alright? Okay. So with this as the pedagogical backdrop, and the pedagogical framework that I will operate within. Let me start talking about this. So this is from an online tutorial by an author called Philip Figari, who writes articles on engineering educational website called Instructables, and he walks in a very stepwise manner through the process of plotting a stress strain curve, alright, and we will all look at it. Now in the last class all of you have seen what stress is, okay. So do you recall what stress is? Stress is sigma, which is force per unit area, okay, and the unit of stress and the unit of pressure, are they similar or dissimilar? Similar, isn't it? And what is the unit associated with pressure? Pascals, and hence Newton per meter square, right? And the unit associated with stress as a consequence would also be Newton per meter square and hence Pascals, alright. So what we are going to plot here is stress as a function of strain. And how many of you remember what strain is? Yes, so that is correct. So strain is basically delta L over L. So I told you that a typical experiment would be a dog bone experiment, wherein what you can do is you can take material sample such that it looks like a dog bone. You clamp it on both sides, and let us say you apply tension across this material. Across any given cross section, I can define a stress, correct? And then I can say, okay, I know the original length associated with the system, and I know the revised length, and this revised length is measured by using something called the strain gauge, okay. So I have the revised length, which is written as L plus delta L. So the incremental change in length is delta L divided by L, and I also told you that the Young's modulus can be defined as stress by strain. You all agree? So this much we have seen in the last class. Do you all recall that? Now I want you to look at this figure. So this is an example of illustrative learning. I am not going to describe the figure to you, but you will get a chance to discuss with one another and describe the figure to one another. So I am saying that I am going to do this dog bone exercise. It's called the tensile stress test, alright, and I am going to plot sigma as a function of strain, stress as a function of strain, and this is the feature that I am actually going to observe. So what you are going to do are three things. Number one, you are going to describe the features of this curve, okay. You are going to describe the features of the curve. You can also talk about mathematical properties of this curve. This is non-linear, this is linear, this is quadratic, whatever. It looks linear, it looks quadratic. You can actually be very free and talk to one another about the way you describe this particular figure, number one. Number two, identify salient features of the figure, and based on the labels provided, come up with a definition of these labels. You understand? I am not going to define these labels for you. I have already marked the curve, and I am asking you what the physical interpretation of each of these labels would be. You understand this? You understand this? So I am not going to define any of these things written there. I have a curve and I have put some labels. You are going to define these labels for me. You understand? You follow? So why don't you discuss with one another, spend a couple of minutes with one another and help things discuss with one another, help one another. So for example, to begin with, you can take this. We will talk about the top two later. As of now, we have discussed stress and strain, agreed? So why don't you discuss this 1, 2, 3, 4 for the time being. That means run, rise, yield strength, ultimate strength and fracture. That is all. Spend a few minutes discussing with one another. Do you understand the question? Good. Yeah. So please discuss with one another. So start labeling it as you see it. you can describe the nature of the curve to one another and use your descriptions to define the labels. You understand? So teachers, please note this is an example of something called scaffolding. So there is usually a lot of complex information that is given to students. Very often they do not have the mental framework to understand these complex things. However, when you give them enough props, when you give them a scaffold, a framework within which they can actually put this large number of information together, they get to consolidate information better, absorb information better. And this is actually an example such as that. It's called scaffolding, and it is due to a person who researched education called Vygotsky. So can you describe the curve to one another at least? How would you describe this curve to one another? So can you define Young's modulus uniquely everywhere? Or is there a limit the way it is drawn? Yes. And where is the linear region? First question. Then, okay.
This is the point where this linear relation.
So what is happening physically? So I am taking a dog bone, I am going to actually apply stress across it. I am observing strain, right? And it's linear for a while and then it becomes non-linear. Why would it become non-linear? What is happening there?
Deformation.
There is deformation. Okay. Keep thinking. And why do you have this? What does this mean? Will all materials show that? Some materials show that? Yes? Do you understand? So, yes. Please tell me, how is it that you are describing it? Very good. Very good. So this is the rise, this is the run. Go very slowly. So, can you define Young's modulus throughout? Number one. Number two, what are the mathematical features? Is this linear, this non-linear, this non-linear? What is happening? And why do you have positive slope here and negative slope here? You understand? When you are thinking of it mathematically, you should think in terms of slopes, curves, linear or not, quadratic or not, things like that. You understand? So where is the linear portion? If so, why? Where is the non-linear portion? If so, why? What are the slopes associated? If so, why? And you have a dramatic change in slope. If so, why? At least there are two regions where the slope is zero. Yeah. Why would that be the case? Surprising, isn't it? Do you understand? Yes. So the author who gave this exercise also has asked these questions. Is this material brittle? Is it ductile? If so, to what degree? What loads can it withstand before it breaks? Breaks is when the material snaps, it ruptures, it fractures. Okay. So right now we don't have any numbers on the x-axis and y-axis. Right? So shall we start defining a few things? So most of you got one thing very clear. Run by rise is slope and that is defined here in the linear region. Correct? The Young's modulus and hence Hooke's law is defined strictly in the linear region, and stress by strain is clearly the Young's modulus. That thing you have actually gotten it very clearly. All of you figured that out very good. Now what about yield strength? What is yield strength?
So the point at which the linear relationship is not there, that means it's not obeying the, restoring force. That restoring force is not working properly.
Correct. So beyond this, there is permanent plastic deformation. Below this yield strength point, there is the elastic limit. So this is called the elastic limit. So wherever this law holds true, that region is called the elastic limit. You understand? So below the yield strength, you can anticipate elastic behavior. Beyond the yield strength, you anticipate dash behavior, plastic behavior. Now, elastic deformation, is it reversible or non-reversible? Perfectly reversible. You can see it, right? But what about plastic deformation? As you have seen around, can it be reversed or non-reversed? Or is it irreversible? It is irreversible. So, you just observed a few things. Elastic deformation is reversible. And plastic deformation is irreversible. And the elastic limit corresponds to the region where the Hooke's law is true, and hence stress by strain is well defined. That is the Young's modulus of the material. Now, notice this. There is a sudden change in slope there. Correct? What is that sudden change in slope? What might be happening? And what kind of material is this? By looking at it, can you tell me whether it's likely to be a metal or a ceramic? Just by looking at it. Discuss with one another. You can look at the properties of ceramics as it has been written to you and given to you in the form of handouts. Read the properties of metals, read the properties of ceramics, and tell me whether this stress strain behavior corresponds to a metal or a ceramic. And then we'll come back to the scaffolding exercise. Okay? Because you're making progress. Good. So please discuss with one another, Malay and Naveen, please discuss with one another. So do you understand the question? There is a sudden change in slope here. Why would that be the case? So read material on mechanical properties I have given or of classification of materials based literature I have given and see whether this is likely to be a ceramic or a metal. Is this a ceramic or a metal? So these two are what I want you to read. So can you at least identify the keywords associated with metals and ceramics? So what are the keywords? Malay. Very good. So when you look at that, does it look like a ductile material? Or does it look like a brittle material? A ductile material is something that can be drawn into a wire, whose length can change dramatically. So does that look like something which is drawn or something that is just rupturing past a certain elastic region?
It's ductile enough because after a certain time.
Very good. Very good. Very good. So let me come here. So have you decided whether it's a ductile material or a brittle material? It's a ductile material. Very good. So the fact that you have your stress by strain, there is a change in slope and we have still not defined what it is. We still don't know what it is. Yeah? But there is a region where the slope is positive, followed by a region where the slope is negative. But then there is a point beyond which you cannot even define strain. That is because it basically comes apart. So this is what is actually called the fracture point or the rupture point. This is what is called as the ultimate tensile strength. Correct? This one was called the yield strength. This one is the elastic limit. This is called the elastic limit. And this region of positive slope and this region of negative slope will also have to be defined soon enough. Correct? We have not defined that yet. And we have to come up with a physical interpretation. Now most of you came up with this answer independently. You said that it's a ductile material. Correct. Because think about it, the strain is substantial. That means you are taking the wire, you are applying the stress, and it's actually elongating. It's actually elongating. It's not just ruptured. So this is clearly the stress strain curve corresponding to a material that is ductile. The opposite of ductility is brittle nature. A ductile material, the opposite of that would be a brittle material. Alright? So ductile, the antonym of this is brittle. Now that you know the difference between ductility and brittle nature, ductile material and brittle material, think about what you would anticipate if you did a tensile stress test on a brittle material. So you understand the question? I don't have the data for it, but even before you do the experiment, can you predict what the stress strain curve would be for a brittle material? Okay, so try. Please try. You understood the question? All of you have understood the question? Very good. Go for it, write down. And go back to the classification of materials. Look at the numbers and let that number get reflected. For example, the Young's modulus of a brittle material, Young's modulus of a ductile material. What do you expect? Where do you expect higher slope? Let it reflect in your graphs. You understand? You understood? So let it be as physically reasonable as possible. So for example, here is 40 to 400, here is 150 to 450. So which one is likely to have a higher Young's modulus? Ceramics. So let that be represented. And ceramics tend to be brittle, right? So you can choose a sample material which is ceramic, right? Draw a curve that corresponds to a higher Young's modulus. Then you have to choose how much elongation you will allow before it ruptures. In the case of the ductile material, you will have to choose how much elongation you would actually allow till it ruptures. Please plot it. You understood the question? So it should be physically reasonable. Now, in the same stress strain curve, plot for a ceramic material and plot for a metallic material. You will have to choose which one will be brittle and which one will be ductile. Which one is likely to be brittle, which one is likely to be ductile. Okay? Which one will have higher slope, which one will have lower slope. And you will have to choose the allowed strain before which rupture will happen. You understood? So can you discuss with one another? All of you are doing very well. You will have to explain your thinking to one another. Now you compare your answer with what is given here in the board. See if it makes sense to you. Does it make sense? Does it not make sense? Can you discuss with one another the features on board? Where is it that you are finding similar features to the one that is there on board? Where do you have dissimilar features? And explain to one another why that would be like this. Like some of you have similar features to that what is given in the board. Some of you have not gotten it. So explain to them. Okay? Yes. You understood? Yeah? So, to begin with, notice that this is likely to be a ceramic material from our classification. This is likely to be a metallic material. This one has higher slope, which is consistent with the fact that ceramic materials have higher Young's modulus. And this one has lower slope, again consistent with the fact that when compared to ceramics, the metals have lower Young's modulus, and hence this slope is likely to be small. Remember, this is strain and this is stress. Okay. Now you have this as defined as the linear region, that is the elastic region. This is the elastic region. The elastic region corresponding to the metal versus elastic region corresponding to the ceramic. Which one is larger?
Metal.
Here, the slope, if I looked at the yield point, this will be the elastic region. If I looked at this would be the elastic region. Which one is larger? Likely to be larger? Metal. That is also reflected here. Correct? And you also saw that ceramics, they tend to rupture rather quickly in tension. That is happening. Metals don't rupture that easily. They are ductile, which means there is flow of material here. There is deformation, there is plastic deformation, and there is substantial region over which plastic deformation happens. Here on the other hand, the plastic deformation is not happening over a substantial strain range. You understand that? So please try to capture these things in your figure. Got it? Got it? So brittle material in comparison experiences very little plastic deformation. And it also has a relatively narrow range when it comes to the elastic limit. These are the two things that you have to capture. Over and above that, the Young's modulus is higher. And it ruptures rather quickly. Okay, these are the facts that need to be accommodated in the qualitative nature of these graphs. You understand this? Good. Alright, so let us get back to the first instructables instruction. So have you labeled your axes correctly? Have you depicted your Young's modulus reasonably? Do you understand what yield strength is now? It is the maximum stress beyond which plastic deformation occurs. The next couple of things are relatively new. Strain hardening, max tensile strength, and necking. Now look at the nature of this graph and explain to yourself what this might mean. So this is considered the region of strain hardening. This is considered the region of necking. Okay, and this one is called the ultimate tensile strength. What do these three terms mean? Can you define it based on the features that are present in the graph? You understand? So why don't you discuss with one another? Please discuss. Turn to one another. The slope here, is it less or more when compared to the slope here? The way it is drawn.
It is only linear, it is not linear.
Huh?
It is exponentially increasing.
Slope is less.
And how does this compare with, so here for example, what would your interpretation be? What might be happening there? See, it's actually going down. So that's really surprising, isn't it? That means you are saying that you are gaining length without even applying the original amount of stress. What might be happening? What is that event? I take a piece of wire, I keep applying stress, it keeps becoming bigger, and beyond a point what is happening is I don't even have to apply that much stress, it starts flowing. That's what it means. After that I have to continue applying some stress. You understand? So what is really happening? Do you understand this question? So just the questions are the following. That is, by looking at the nature of this curve, can you explain what each of these regions are? What might be happening? What might be happening? You don't have to know the full physical mechanism, but what might be happening based on the language you have learnt in this class. That's all. Okay, discuss with one another. So what have you learnt? What have you deduced?
So that is positive slope, but lower slope than the elastic region.
Yeah.
And then after in making the negative slope, that means the stress is,
Yeah.
you don't have to give much.
Yeah, so something is happening to the wire. Okay, otherwise it would not necessarily go down, isn't it? So past this yield point, past this yield strength point, something is happening to the wire. Otherwise, why would you have to apply lesser stress and why would you get so much elongation? It doesn't make sense. So the nature of the wire is changing. Something has actually ruptured. Correct? You understand? So that phenomena is called necking. It's not rupturing, it is necking, wherein there is a region of the wire that basically becomes thinner, slender. And because it becomes thinner, the stress acting at that particular region is fairly high and hence it will start flowing very quickly. So it is not the true stress. It is the engineering stress. It is the engineering stress as defined by that particular dog bone experiment. I am basically having a constant area in the denominator. But the truth is it is not a constant area experiment. So you have to actually correct for it and get the true stress, in which case you wouldn't find that negative slope. You would actually find a continuous region. Yes. Yes. What do you find? So what is the ultimate strength as far as you are concerned? So ultimate strength, beyond that, what happens to the stress strain curve, the slope of the stress strain curve? It becomes negative, right? So what does that mean? You have to apply progressively less stress to get very large strains. So that means it's just flowing, and beyond a certain point it snaps. Correct? Correct. And then what is this region, strain hardening? What does it mean? So to begin with it was supposed to flow, but after that it is not easily flowing. Correct? So after the yield point, you are right. There is a region of marginal negative slope, and that corresponds to the necking. So if I take a wire, if I take a piece of wire and I apply strain, this is stress. I apply tensile stress across it. Now I do expect sigma by epsilon to be positive, of course. There is no question about it, and it's constantly positive if you think about it. What might become negative is d sigma by d epsilon. That can become negative, as you can see. The region where the d sigma by d epsilon is becoming negative for the first time is what is defined as the yield point. See, look at that, isn't it? So that's also the region wherein a neck starts forming. Correct? Do I understand what you are thinking correctly? Alright. So actually the area of cross section here has reduced, and hence though you are applying what seems like a smaller stress, it's actually a substantial stress here, and as a consequence the material will start flowing here. This region will have very dramatic movement of material because you are applying a lot of stress there. There is a stress amplification that is happening there. Do you understand that? But then after that, that region actually becomes pretty strong, and that is called strain hardening. So you will find that it is not continuing to decay. It's not soon after this, it is not necessarily progressively coming down. It's actually bouncing back. You understand? It's bouncing back, and that is because there is something funny that is happening in this region primarily and in the regions around it. Okay, so that hardening is called strain hardening, and that is what is written there. There are other names for strain hardening, and I will show you those names, and you should write those names down. So these are the other names associated with strain hardening. Please write these names down. It's also called work hardening because you are working on that region. Okay. It's also called strength hardening, or it's also called cold working. So strain hardening, cold working, work hardening, strength hardening are all the same thing. Okay? They can all be used interchangeably. And finally, you have the necking region, right? So finally you have the necking region. That's the region wherein the material is caving in, it's flowing very dramatically, and so on and so on. You understand? You understand? Now, in the description that I have given you, I have made a mistake, and very deliberately. Can you find out what mistake I made in the discussion? So the way in which the plot shows, necking is in one region. The way I described, I assume that necking is in another region, okay, in another region in the plot. What is wrong about the way I described it? Can you actually discuss with one another and find out the mistake in the way I described this plot? You understand? So I made a mistake, it was very deliberate. You understand? And I want you to find out what is the error, and the mistake is on the board. And it was a deliberate mistake. So where is necking happening? Objectively, it is happening beyond the ultimate tensile strength. That is the fact that I did not take into account while describing it. Necking is happening exclusively at that point. You understand? And hence the slope is negative. In the other case where there is a change in slope, that change in slope is actually a determinant of the region beyond which plastic deformation is expected. Okay. Now, but notice that it is very interesting. This region, okay. So that is the region that comprises of the linear region plus something called the 0.2% offset. It's called the 0.2% offset. So whatever is the strain at this point, 0.2% of that strain I am going to actually take and draw a parallel line. Okay. So this is called the 0.2% yield strength. So it turns out that materials are such that you can take them beyond the linear region a wee bit and still it comes back elastical. So this is the limit, the elastic limit. You followed. So, but the necking exclusively happens where? Beyond the ultimate tensile strength. But work hardening definitely happens here. Work hardening happens because of plastic deformation. You follow? So now you discuss with one another all the features that are there in this particular graph. So what are the features of the graph? Linear region. Linear region defined by the yield point. Then you have the plastic deformation and hence the strain hardening or the work hardening or the cold working region. Then you have the necking region, then you have the rupture. Alright, and this is a typical graph corresponding to a metallic or a non-metallic material? Metallic material. You understand? So the reason why I mentioned this is because very often in your practice of materials engineering, or for that matter engineering and science in general, you will need to come across graphs. You need to be able to interpret graphs. You need to be able to use graphs to get some complex information, make some inferences. You understand? So next time whenever you run into graphs that are being described, ask yourself, is this the right description? I gave you a description and there was a deliberate error there. But out there in real world, in textbooks, in literature, there may be real errors that actually make it there because of the error from the author. It's very important for you to actually invest your time and ensure that your inferences are reasonable. Another thing is the data that is being plotted. How do you know whether it is reasonable or not? Okay, so you might want to actually test, evaluate, check the reproducibility of data. Multiple people may want to actually check the reproducibility of the data so that you get confidence in the data. An experiment like the one that is actually given there, there could be multiple things that could go wrong there. So many things could go wrong. So it's a good idea for you to check for reproducibility when you are doing it in your laboratories. You understand? So when you do a laboratory experiment such as the tensile stress test, next time when you plot it, analyze what is happening. What is the linear region? What does Hooke's law tell us about the Young's modulus? What is the yield point? How do you define the yield point? What is the strain hardening region? What is the necking region? What is the rupture region? Do they all make sense? How does it compare with that of a brittle material? Now I will give you a homework wherein you have to actually do a reading exercise. You are welcome to use any search engine of your choice to actually find answer. So instead of doing it for a metal or ceramic, we will do this experiment on a polymer. So I am going to actually make this dog bone using a polymer. I am going to cast a polymer and make it. You understand? And you are going to actually tell me what you expect. And you interpret that particular curve. Alright? Now I will add 2 layers to whatever we have shown or discussed in the classroom. And this is the true stress versus true strain curve. Okay? And here what happens is that there is absolutely no region of negative slope. Why do you think there is no region of negative slope? And based on that, can you tell me what the definition of true stress is going to be? It is the instantaneous stress, okay, which is the applied force divided by the area. So if there is a necking region, there is a reduction in area, and that area is what is actually put in here. And as a consequence, there is absolutely no region of negative stress. Or there is no region where d sigma by d epsilon is negative. Okay, so d sigma by d epsilon basically remains positively sloped all through. You understand? Okay, and I want to show you this graph. Okay, now this is a graph that shows you how a material can be strengthened further. You have been given some material. It has some finite strength. I want to strengthen it further. Okay, use this graph as a clue and tell me how you would strengthen the material. You understand? So please discuss with one another. So again you have stress on the y-axis, strain on the x-axis. You have to tell me what these loops correspond to. Okay? You understand? You understand the question? So please discuss with one another. Are you discussing with one another? So what do you find? So the stress is on the y-axis, strain is on the x-axis. What do you find? Yes. So this is the strain. So let me plot it here for your convenience. What we have is stress on the y-axis, strain on the x-axis, and what we are doing is we are taking it, we are straining it a wee bit, and then we are releasing the stress. And then what we are doing is we are again taking it through this side. I am going to actually apply stress from here. So I am bringing it down. I am going to apply stress again. And I bring strain to this point. Okay. And I keep doing this. So I am basically bringing it down, bringing it up, taking it further, bringing it down, taking it up. So what I am doing is I am applying stress, releasing the stress, applying the stress again, releasing the stress. Each time the slope, as you can see, is different. Why would that be the case? Why would that be the case? The way it is shown, the slope is becoming slightly different, right? Why would that be the case? And what advantage would it give you?
The brittle part is increased.
Huh? Is that what is happening? Is the Young's model is increasing, decreasing? What is happening? So you just learned something about strain hardening. Based on strain hardening, what do you actually infer from this curve?
TIJU modulus is almost same or decreasing a little.
Yeah, the way he has shown it here, you can actually make it a little bit more clear. The material, you are deforming it plastically, and it's permanent deformation, so it stays there. Then you are applying some more stress. It's undergoing further plastic deformation. What are you doing to it? You are applying progressive strain hardening. So will the Young's modulus increase or decrease? Increase. So you can start with a material that doesn't have high Young's modulus, and you can make it a material through plastic deformation that has high Young's modulus. Now write down this as a homework question. How can you achieve some applications of this? So you have made a discovery. You can make a material progressively plastically deformed. What application could you have of this? Once again, I would like to acknowledge Andrew Figari for this picture and this content from Instructor. So the question is, what would be the application you could envision? You understand? So I asked you a few homework questions. What are those homework questions? Polymer stress strain curve, and the second one is some applications of progressive strain hardening. And did I ask anything else? And then true stress, true strain. Okay, you find out true stress versus true strain for each of these materials: metals, ceramics, and polymers. All right. So now can you discuss with one another and come up with summary of today's class? That's what we will do in the last 5 minutes of this class. Okay. So please discuss, look at your notes, and come up with summary of today's lessons that you have done. And remember, I made a mistake that was deliberately done to get you to think about the graph. And this time when you describe the graph, it has to be correct. Okay. So you have to get necking region correctly. Alright? Yes. You understand? So please summarize for one another 5 points that you have learned today. 5 points. So what is one lesson that you learned today?
So how to plot stress versus strain.
How to plot stress strain curve.
Then defining this different regions for like ductile and brittle.
Very good.
material.
Did you learn how to read a graph?
Yes.
Okay. Yes. Good. And how the data in the graph can actually tell you things about the physical mechanisms that might be involved, about the physical interpretation of a graph. This is very important regardless of whether you are doing stress strain or anything for that matter. When you are plotting a graph, think, what does it actually mean? Right? It's very important. Yes. Did you understand? So what are some of the lessons that you have learned? Let me now make notes on the board about the lessons that you have learned. So can you tell me a few lessons you have learned? How to plot sigma versus epsilon from both metals as well as ceramics. Very good. And so this one is a brittle material, correct? What's the opposite of brittle? Ductile. Fantastic. Very good. Now, another lesson learned.
Different regions of this tested.
What is that?
Different region of this tested.
So regions of sigma versus epsilon curve. And what are some of the regions that you learned? So elastic limit.
Yield strength.
Then yield strength. Ultimate tensile strength. Fracture point or fracture strength. What? Yeah. So you learned about strain hardening. It's also called cold working or
Strength hardening.
Huh?
Strength hardening.
Strength hardening. So it's all the same stuff. Hardening. Cold working. Or work. So I put it all inside a bracket, a bracket. So you learned these things are all synonymous. Then what else did you learn?
Necking.
Necking. Okay. And more. Then
True stress.
so the other one is called engineering stress. When you measure it, it is called engineering stress. So engineering stress versus true stress. And d sigma by d epsilon, can it be positive in this and negative? Positive and negative. In which one? So if I have engineering stress versus strain and true stress versus strain, where am I allowed to have a negative slope?
So engineering.
Engineering, right? In the other case, you will have continuously positive slope. You understand? Now, here you will have a continuously, beyond necking, by the way, this is very important. If you correct for this, how would the graph change? This is important for you. How would the graph change if you corrected for the cross section? So this is another question I want you to think about. So write down engineering stress versus engineering strain, and true stress versus true strain, all the salient differences that you can anticipate. So with that, we have come to the end of this session. So we will see you all shortly again.